Hey guys, good morning. Mr. Letty here, going over our notes for Plate Tectonics, day number 2. Just adjust the microphone here. All right, where we left off, Alfred Wegener had just proposed continental drift, and when he presented it to the scientific community, they asked him how the continents moved, and he had no answer. Okay, so that is where we left off, and let's get through this. Okay, so Wegner presents his theory. Unfortunately for him, World War One breaks out. So nobody from the English or French or American sides really care what a German scientist has to say, as we are currently at war with them. So we go through World War One. We go into the Roaring Twenties. Then we go through the Great Depression, followed right into World War II. Okay, so a lot of things happening between 1916 or so and 1945 that pretty much puts a halt to a lot of scientific discoveries as far as non-military things go. All right, but World War II ends. Okay, and we are left with a tremendous amount of Navy ships that we have built. Okay, so a lot of these ships were equipped with something called sonar, which is being able to track things with sound. Okay, and we're very concerned because now Germany's no longer our big enemy, it's the Soviet Union. And we're very concerned that they are going to be able to park submarines right off the coast of New York or Washington, anywhere up and down the East Coast and the West Coast. So what do? We decide we're going to map the ocean floor so we can kind of figure out where submarines would be coming from, what would be their best path to get here. So basically, again, looking at the ocean floor so we can kind of figure some of these things out. All right, so here's how we do this. If you look at our first slide, you have our ship here, which was a gunship, so you see the guns in the front. Okay, and it had its sonar. And we sent these ships out with scientists so that they could go and map the ocean floor. And here's basically what happens is on the bottom here, in the middle picture, we have a ship that has a little transmitter, and it shoots out some sound, which bounces off of whatever we're aiming at, and it shoots it back. Okay, if we know how fast sound travels, which we do, and we know how long it takes for it to get back to us, we can figure out how far away we are from whatever we're looking at. So in this case, the ocean floor. Okay, so that's kind of what we're doing is these ships are going around and we're bouncing sound all over the place. All right. If you were whales, that probably was very annoying, but, you know, it is what it is. Okay, pardon me as I move myself out of the way. So here is a picture taken by sonar, and this is what we find. We're expecting that the floor of the ocean is going to be a flat, desert-like, no real features, just some sediment in a flat, vast floor. That's not what we find. All right, what we find are mountain ranges, huge mountain ranges. All right, so once we find this and discover this, and it's not just in one area, it's all over the place in the ocean, these scientists start to study the ocean floor because this is a weird discovery. It didn't line up with what we thought should be there. Okay, so we look into it. And as we look into it, we figure out a couple of things. Okay. So, sorry, moving myself again. All right, so what did we find out? Oops, that's one too many. Okay, so unlike the continents, which were primarily made out of granite, we find that the ocean floor is made out of basalt. Okay, and basalt, which, if you remember from a couple of months ago, is an igneous rock. Okay, it is rich in iron, which is Fe on the periodic table, so it has a lot of iron in it. Okay, and it's denser than granite, so it has a higher density. Okay, what we're concerned about is the iron content. Okay, so as the magma comes up from the bottom of the ocean, which if you look here in the bottom left, the orange is obviously the magma. It comes up, it hits the cool ocean water, and it starts to solidify. Okay, so we're making new floor. Okay, the iron is going to be pointing, because iron is magnetic, so it's going to be pointing north. All right, so if we take this pen here, all right, and the tip of the pen is pointing north. All right, so we study the ocean floor, and all the little pieces of iron are pointing north. But then as we go, I don't know, let's say a couple hundred feet out, we find that all of the iron is now pointing south. Okay, and then we keep going, and then it flips around and it's pointing north again. So we check the other side of the ridge, and we see that the pattern is the same. Okay, now the width of each section is not necessarily the same. So it could be 50 feet, it could be 100 feet, it could be 300 feet. Okay, but eventually the iron would point in a different direction. Okay, so what this is telling us is if we look here, we're going to talk about something called polarity, which has to do with magnetism. So normal polarity is what we're going to consider pointing at the North Pole. We're considering that normal polarity because we're in the northern hemisphere right now, and that's the direction it happens to be pointing. So we assume that's normal. It's really just the way we happen to pick it. So that's the dark blue stripes. And then the light blue stripes are going to be reverse polarity, where it's pointing towards the South Pole. Okay? So as time increases, we see that these stripes become more and more frequent. And what's happening here is as the new ocean floor is coming up, it's pushing the ocean floor on either side of the ridge further away. Okay? So, if we're pushing it further away, then that leads us to discover that the ocean floor is not the same age all the way across. Okay, as a matter of fact, towards the middle of the ridge, it's very young. As we move away, it gets older and older and older. And the oldest spot is going to be the spots that are touching the continents. All right, so where the ocean floor moves and it runs into the continent, okay, that spot right there, right here, that's where the oldest ocean floor is going to be. Okay, so that's a little weird for us to comprehend that a flat, relatively flat piece of ocean floor is not the same age as we go from west to east. Okay, so that causes somebody by the name of Harry Hess. Okay, so he's a scientist in Princeton in New Jersey, and he uses this evidence to develop the theory of seafloor spreading, which I just kind of explained to you, but we'll go over again. Magma comes up, it's hot, it hits the cool ocean floor, forms new crust, and it is pushed to the left and the right away from the middle of the ridge. Okay? This causes the ocean floor to move towards the continents because it is denser. Okay? Remember I said that when it hits, so I have the ocean and I have the continent. So as the ocean comes towards the continent, it's going to go underneath it. Okay? Because it's denser. All right? Well, that movement going underneath is going to push it. So the continents are going to start to move away from each other. So in this case, if we looked at the left, this would be North America, and on the right, it would be Europe. Okay, so we're moving further and further away, or South America and Africa. Okay, so you're getting this cycle that's moving like this. Now this crust comes down back into the upper mantle, where it melts, becomes magma again, and as it heats up, it eventually comes back up and becomes new floor. So the old floor is going to melt and help build the new floor. Okay? So seafloor spreading. All right, move myself back down to the bottom corner here. Okay, so what does that tell us? Well, hold on, move me out of there. So this means that Wegener was actually right. He didn't know how it worked, but if we combine isostasy, so the continents floating on the magma, continental drift, so Wegener's theory that because the fossils, the diamonds, and the puzzle pieces, that the continent was once connected in a supercontinent called Pangaea, okay, and sea floor spreading, we add all of that together and we get plate tectonics. Okay, so here's Wegener, weirdly, as he got much, much older and he's dead at this point, he knew he was right. Okay, all right. So, I'm going to give you the theory of plate tectonics very, very quickly in a nutshell. Okay, so the Earth is covered in lithospheric plates. So the lithosphere, which is the top part of the crust, or the crust in the upper part of the mantle. Okay, think about when you bake brownies and you see all the cracks right on the top of the brownies. Okay, each one of those little sections is like another plate on the Earth. Okay, each plate has a different density and makeup. All right, where the plates meet, we call those plate boundaries. And when it's a boundary, remember that's an interface in between two things. So it could be two continental plates. It could be a continental plate and the oceanic plate, or it could be two oceanic plates. All right, so those are combinations. And depending on what's going on, different things happen. Okay, and the different things that happen will tend to be the cool things that we want to learn about. Okay, so we're going to go more into those next week, but those will be the things that are a little bit more fun. Okay, so let's talk about some of these plate boundaries. All right, and I'm going to move myself yet again. Okay, so convergent plate boundaries. To converge means to come together. So these are when two plates collide directly. So they smack into each other head on. Okay? If it's two continental crusts, like the bottom picture here, you're going to get wrinkles, which those wrinkles are going to become mountains. Okay? If it's two oceanic crusts, you're going to get a little trench. Okay? And you will start to get some undersea mountains as well. And if you get the oceanic crust and the continental crust, not only do you get mountains, but you tend to get volcanoes. Okay? Now, the other thing to keep in mind is anytime we're talking about two plates colliding, when they collide, they release energy. You know that energy releases another term. Those are earthquakes. Okay, so we're going to learn a lot about earthquakes, as I said, next week. All right, so a lot of this stuff all has earthquakes associated with it. All right, then we get into... Oh, I'm sorry, wanted to cover this. A subduction zone. Okay, so this continental plate on the right, we're going to call the overriding plate. This is the plate that's going to stay up top, and it's because it's less dense. So continental crust tends to be made out of granite, so you're going to hear it called granitic. Okay, and that is less dense than our ocean crust, which is basaltic. Okay, so oceanic crust, basalt, more dense. Because it's more dense, goes underneath. As it's scraping by the continental crust, it's heating up. So we start to get these little drops here of magma, which are going to collect in a magma chamber. Okay, and we're going to have a volcano forming here. So along the mountain ranges, like the west coast of the United States, where we have the Cascade Mountains, in California going up into Washington and into Canada. You have the Rocky Mountains over there. There's concerns of volcanoes. For us, that would be Mount St. Helens in Washington State. But that doesn't mean that that's just the only volcano there. That's just the most recent one to erupt. We have many more volcanoes on the West Coast. Okay. So now, as this one plate goes underneath, you're going to get a trench. So it's going to think of like a V. Okay. And this is where, and this picture doesn't really show it, it should more come down. Okay. That's going to be your deepest parts of the ocean. All right. And the famous one that you may have heard of is the Marianas Trench, which is off the coast of Japan. Okay. That is the deepest spot in the ocean. And that is about 7 miles deep. To put that in perspective, Mount Everest is about 5 miles high. So if we could cut Mount Everest off at the base, flip it over like an ice cream cone, and drop it into the Marianas Trench, by the time it's settled, there would be 2 miles of water on top of it. So it would sink, and the very top of it would be 2 miles from the surface of the ocean. Okay, so that's how deep it is. All right, so that's our subduction zone. All right, divergent. Divergent means to diverge, means to go away or to separate. All right, so these are two plates that are moving away from each other. This would be like in the middle of the ocean. All right, so we have the Mid-Atlantic Ridge. Okay, so the two plates are separating. This is where the new seafloor is forming in the seafloor spreading example. Okay, and it separates. Okay, so that's our new ocean floor. Not a whole lot of earthquakes here. This tends to be relatively calm compared to some of the other plates. All right, but these are out again, tend to be in the middle of oceans. All right, then we go to our transform plate boundaries. This is the third one and the last one you're going to have to know. All right, this is when two plates are sliding past each other. So they're not crashing in. Figure that they're next to each other, okay? And one is going this way, and one is going that way. So we have this happening, okay? This is where large earthquakes happen, all right? The way I kind of like to explain it when we're in class, if you make two fists, okay, and you put the fists together so that your knuckles are interlocking, okay, and you're pulling one fist towards you, do not punch yourself in the face, even though I would find that pretty funny, okay, and you're pushing the other fist away while you're pushing them towards each other, okay, so it doesn't want to slide because your knuckles kind of lock in, but when it does and your fingers move over, that release of energy where it finally gives way, that's the earthquake. Okay, so this is going to be like the San Andreas Fault in California. All right, very, very large earthquakes. All right, that doesn't mean you can't have smaller ones. Just to put it in perspective for you, in a given year, so 365 days, you could expect that somewhere on Earth, about 2,000 times a year, there's an earthquake. Most of those earthquakes are so small you don't even feel them. Okay, it's the larger ones that we tend to recognize and feel. All right, and that's going to bring us to page 5 of our reference table. So we'll go over this real quick. All right, and then I'll pick this up again tomorrow. All right, so if we're looking at page 5 of the reference table, which is called tectonic plates, you're going to see the names of all the plates. Okay, so pretty straightforward. We live on the North American plate. Why don't we get a lot of earthquakes here in New York? Well, we're right where the arrow is, and you'll notice we're nowhere near a plate boundary. All right, so those plate boundaries are where the earthquakes tend to happen. Doesn't mean it can't happen elsewhere. Just the majority of them happen there. Okay, so our plate boundaries of the North American plate, if you look at this arrow here, and this arrow here, okay, and this arrow here, is moving out and curling. All right, so that's how this plate is moving. The Eurasian plate, which this part is Europe, moving away from us. All right, so we are moving towards the west. Europe is moving towards the east. Okay. Right here's the San Andreas Fault. You can see the arrows sliding past each other, which if I look down here tells me transform plate boundary. Okay. If I look here at the Aleutian Trench, which is out near Alaska, those are two plates that are crashing into each other. Okay. So this is a converging, which is this guy over here. And you see how we have these little black boxes? All right. The black boxes are telling you which plate stays above the other one. So in this case, the northern part, which is going to be the Aleutian Islands out here for Alaska, okay, and the northern part of Russia, that stays above as the Pacific plate is going underneath. Okay. We have the Mariana Trench over here. This whole shape here that I'm tracing out, okay, that's the Ring of Fire. Okay, so we read about that earlier. All right, and you get to basically just see the idea of wherever the arrows are going, it tells you which way the plates are moving. All right, so we're going to end there for today. Hope everybody's staying safe. Hope you enjoyed this week's work because it was relatively light. Next week, not so much. You're going to have a little bit more to do, but it should be a little bit more interesting as we're going to be looking into things like earthquakes, tsunamis, and volcanoes. All right, so I will talk to you guys soon, and have a good day. Bye.